Okay, so homework. All right. So today we're going to start off with just a little piece of single replacement that we didn't get to last week. It's not a big deal. We talked about it. We just didn't give you the activity series for it. Although I did give you the activity series. Okay, because most of the ones you did had metals. We put metals and non-metals. We took metals and metal compounds and put them together in the lab. Okay, but got to remember that non-metals can replace non-metals too. Non-metals can replace non-metal, but we don't have as big a list this time. Okay, it's not every non-metal. There is a system. We're just not going to use it. Okay, but we're going to limit ourselves to the halogens. And I really don't have to give you an activity series for it. It's printed down here at the bottom. But if you look at what's printed at the bottom of your activity series for the nonmetals, it's in exactly the same order as the periodic table. F's on top, I's on the bottom. F's on top, I's on the bottom. So the most active replaces the least active. The top replaces the bottom. Senior girls can replace freshman girls. Freshman girls can't replace senior girls. So that means fluorine never ends up alone. Iodine always ends up alone. It starts alone, it stays there. If it's got a partner when it starts, it gets kicked off. So high replaces lower. So F2 plus HCl. The first thing you have to recognize is that F is a non-metal. Non-metals replace non-metals. Mr. Green? Yes. Yeah. Where are we? What? The 17th. To 17th. 18th. Right. Okay, sorry. Somebody had the wrong date. Okay. So, is this going to happen? Well, fluorine, the nonmetal, is going to try to replace chlorine, the nonmetal. Can fluorine replace chlorine? Yeah, because fluorine's above chlorine, so it's going to happen. So the H starts off next to Cl. It's going to end up next to F. And Cl is going to be by itself. I did my single replacement. Then I have to write the right formulas. H is 1 plus, F is 1 minus. That's the right formula for hydrofluoric acid, or hydrogen fluoride if you've got a gas. And Cl, can Cl be by itself? No, it gets a 2. It's one of our gens, the halogens. And that's going to happen every time with these. So I got 2 Cl's, I got to put a 2 in front of HF, or HCl, which means I got to put a 2 in front of HF to get it balanced. Br2 plus KCl. So we got to look at the thing by itself as a nonmetal. Is it going to replace a nonmetal? So Br is going to replace Cl. Is Br going to replace Cl? Br is below Cl, so this reaction is not going to happen. Hugely different than what we were doing before. Just change the other parts using a different list. Metal activities won't work when you're working with nonmetals. Surprise, surprise. Okay. The fact that they called the first one single replacement implied that there was another kind of replacement, and it's double replacement. Okay. And this is the things that replace is they replace each other. So they swap partners. So in our dance analogy, okay, this is a square dance. Pick your partner up and down, pick her up and throw her down. Now the man left. Change partner. We're just going to change partners. Okay? So I need to have a partner when I start. Everybody's got to have a partner when they start, so I need two compounds, either acids or ionic compounds. People with partners. Most often this happens in solution. So NaOH and FeCl3. I recognize it's double replacement because I got two compounds. And they didn't tell me it was combination. And the way I look at it is the positive ions change place. So it used to be metals replace metals, now metals replace each other. So Na was next to OH, now it's next to Cl. And Fe was next to Cl, now it's next to OH. Notice I don't bring the subscripts with me. I figured those out on the other side. So how the heck did I know that Fe was 3+? I get it from that side. Yeah, the Cl is 1-, and if it's Fe3+ on one side, it's Fe3+ on the other side. Sense? We're not moving electrons around, we're moving ions around. So that I'm going to write FeOH in parentheses 3. The most common mistake is forgetting those parentheses. Doesn't seem like you need them. And NaCl. But that's not balanced. 1 Na on both sides, 1 OH on the reactant side, 3 on the product side, so I got to put a 3 in front of NaOH. That gives me 3 Nas, so I got to put a 3 in front of NaCl. That gives me 3 Cls, which I wanted anyway, and 1 Fe and 1 Fe.
So does it matter if I put
You could put NaCl plus FeOH3, because remember the plus is and. Green and red is the same as red and green. The only place order is important is before the arrow versus after the arrow. Then order is really important. Okay? So here it is in pictures. Sodiums are all paired up with hydroxides, iron's paired up with 3 chlorides, and then they switch partners. It's actually easy if you think about it in terms of names. I started with sodium hydroxide and iron 3 chloride. I ended up with sodium chloride and iron 3 hydroxide. They just changed last names. Does that make sense? They changed last names. That's all it is. They swap partners. So a little bit different than what we're doing. So let's try it. Right now we're going to assume all of these reactions take place. Talk a little bit later about how we decide if they take place. So I got CaCl2 and NaOH. Recognize it's double replacement because it's two compounds. Well, Ca starts off next to Cl, so Ca is not going to be next to Cl. Ca is going to be next to OH. And Na was next to OH, Na is going to end up next to Cl. Na is 1+, Cl is 1-. So that's the right formula for sodium chloride. Calcium is 2+, OH is 1-. That doesn't add up to 0, so got to make it calcium with 2 hydroxides. That's the right subscripts. Now I got to balance it. 1Ca, 1Ca, 2Cl, so I got to put a 2 in front of NaCl. That gives me 2 NAs, got to put a 2 in front of NaOH. That gives me 2 OHs, which I was looking for anyway. Clue. If you get those charges wrong and write the wrong formulas on the other side, it will never balance. Because if you get the charges wrong, you've created or destroyed electrons. Right? And you can't do that, and it makes it so that these will never balance if you put the wrong formulas in. So if you just keep going in circles and it just keeps getting bigger, go back and check your charges. Okay, so CuCl2 plus K2S. So the Cu is next to Cl2. So it's going to end up next to S. K is next to S. It's going to end up next to Cl. Chloride off the table is 1 minus. K is 1 plus. Off the table, S is 2 minus. If I look at copper, though, I can't get it from the table. I got to get it from the other side. So just what you would do to figure out the Roman numeral. Since chloride's 1 minus, my total negative is 2 minus, my total positive has to be 2 plus. So that copper has to be 2 plus on the right side. It won't let me write it, but I can write over here. If it's 2 plus on the right side, it's got to be 2 plus on, there's 2 plus on the left side, it's got to be 2 plus on the right. Okay. Hey, the formulas are right. Now I just have to balance it. 1 Cu, 1 Cu, 2 Cl, so I put a 2 in front of KCl, gives me 2 Ks. I wanted that anyway. Gives me 1S and 1S and 1 Cu. That's it. They should balance pretty quickly along the way. If they don't balance quickly, you probably got a charge wrong someplace. And we just did this one, the first one, that was basically our example. It was NaOH instead of KOH. And let's try the second one here. Phosphoric acid and calcium hydroxide. So H starts off next to PO4. Instead, it's going to be next to OH. And Ca starts off next to OH. Ca ends up next to PO4. Charges. H is 1 plus, OH is 1 minus. That should be pretty recognizable. It made water. And Ca is 2 plus, PO4 is 3 minus. That doesn't add up to 0, so I got to put a 3 next to Ca and a 2 next to PO4. Since I put 2 next to PO4, I got to put a 2 in front of phosphoric acid. That gives me 6 H's. So I can put a 6 in front of water. That gives me 6 hydroxides, counting hydrogens and hydroxides separately from each other, because it's easier. 6 hydroxides, so I got to put a 3 in front of calcium hydroxide. That gives me 3 calciums, which I wanted anyway. If you do this right, you're going to get to 1, which I wanted anyway. Does that make sense? Okay, so this was phosphoric acid. And acids always start with H. Calcium hydroxide, you may have forgotten that I mentioned it earlier, but everything with hydroxide in it is a base. So acids and bases, both dangerous. Mix them together, you make water. Not dangerous. So that's how acids and bases are not opposites of each other. They just react with each other to make water, which gets rid of the dangerous H plus and the dangerous OH minus. And then things are safer. So that's what happens every time with an acid and a base. Acid would always start with the H. Base will always have that hydroxide. They'll always make water. And that's why they neutralize each other. Okay, so will our activity series work for this? Let's think about it. Will our activity series work? Well, if I pick the first metal and the second metal, if the first metal's on top, it'll replace the second metal, but the second metal will not replace the first one, ever. Right? We'll always have that situation where one will always replace, the other will never replace. So the activity series does us no good. Because the activity series is about changing charge. You start off with something without a charge, a metal. That metal has a charge on the other side. You move electrons around. Okay? Here, we're not moving electrons around. Everything's got the same charge at the end as it had at the beginning. It's just got a different partner. So the activity series won't do me any good. Okay? So what we have to look at is we have to look at the products. So we write the equation and see what the products would be. And it will happen if one of these three things is true. You look at one of the products will not dissolve in water. And that forms a solid, and that solid is called a precipitate. Because if you make a solid in an aqueous solution, that solid is going to sink to the bottom. So it's going to fall down out of the solution, which is what precipitation does out of the sky. It falls down. Precipitation falls out of the sky, precipitates settle to the bottom. It's the reason why we can put a downward arrow for a product. It's a gas that bubbles out. Or something that's not ionic anymore, something that's covalent. And the covalent compound you will make, that you can expect to make, is water. Look for water. That gas that bubbles out is why we can put an up arrow on the product side. Because you make a gas in an aqueous solution, the bubbles are going to leave. Okay? All of these are about getting rid of pieces. Some way the pieces have to isolate themselves from that solution. Either as bubbles leaving, solids leaving and sitting on the bottom, or turning into the water that is the aqueous part of it and got rid of those ions because they're not ions anymore. They're in a covalent compound. So it's about getting rid of the ions. That's what makes it happen. Now we talked about the transition metals with the Roman numerals, that their charge had to stay the same on both sides. Your polyatomic ions don't change from one side to the other either. So leave them together as a group, balance them as a unit. So we'll be able to see if it's water because it'll be HOH. Acid plus base make water. This always happens. Gases are harder to predict. We'll talk about what chemical they're specifically talking about that makes gases. And then the solids, there's a pattern to what kinds of things make solids. So we're going to have to be able to predict what the precipitate is, or identify the precipitate on that product side. Remember, precipitate is the solid formed from an aqueous solution. Okay. To show you what I mean by a precipitate, okay. Here I had it here a second. Oh, this is lead nitrate. Lead 2 nitrate, a solution of lead 2 nitrate. And to it I'm going to add a solution of potassium iodide? Do you believe that there was a reaction that took place there? Yeah. What was your clue? Change in color. And notice not just a change in color. It's now opaque. Light doesn't go through it. Okay? So that means there's solids in here. Okay? Oh, because I haven't mixed it very well. Okay? But if we let these sit, over time, that solid should sink down to the bottom. Okay? So it's a powder at the bottom. It'll be a powder at the bottom if you let it dry. So you predict them if you know some general rules for solubility. So they fall into two categories: things that dissolve, things that don't dissolve. There's 5 rules. You don't have to memorize them. You just have to be able to apply them. Okay? These things are soluble, able to be solution. It doesn't say soluble, it says soluble. So able to be a solution. Not able to be a solid, able to be a solution. Soluble. These are things that will dissolve. These are the things that will not make precipitates. I can give you a couple examples. Potassium iodide and lead 2 nitrate. They were solutions when I started. What's the yellow stuff? Okay. Well, salts of alkali metals and ammonium will dissolve. If it starts off with an alkali metal or ammonium, you can expect it to dissolve in water. So anything out of group 1A or ammonium. That is the only rule that talks about the positive ions by themselves. All the rest are about anions. Salts of nitrates and chlorates are soluble. That also implies nitrites, chlorites, hypochlorites, perchlorates. You can expect the bromates to do the same thing. The iodates to do the same thing. Make sense? So we're talking about all those ones with halogens and some oxygen. Okay? Nitrate, nitrite. Those will both stay soluble. Okay? Salts of sulfates are soluble unless they're with silver, lead, mercury 1, barium, or strontium. Again, you don't have to memorize this list, you just have to apply it. So if my negative ion is a sulfate, it will usually dissolve except with these exceptions. So see, the first one's about the positive piece, the next 2 are about negative piece, the next one's about another negative piece. And that would be chlorides. So silver, lead 2, and mercury 1 again. So that's the list of all the things that will dissolve. None of these will be the precipitate. Things that are insoluble, not able to be solution. These are things that will form solids. What that yellow stuff is over there. Hey. Carbonates, phosphates, chromates, sulfides, hydroxides. So chromates means dichromates. Phosphates means phosphites. Carbonate, yeah. There's no carbonate. sulfide, hydroxide. Okay. But now we have now we could run into a potential conflict. If I had sodium carbonate, rule number 1 says because sodium's an alkali metal, it will dissolve. Rule number 5 says because it's a carbonate, it won't dissolve. Which rule wins? Well, they put them in order for a reason. Rule 1 wins all the time. So all those things that won't dissolve will dissolve if they got sodium or potassium in front of them. Potassium carbonate will dissolve. Sodium phosphate will dissolve. Lithium chromate will dissolve. Cesium hydroxide will dissolve. If you could find some francium sulfide, it would dissolve too. You probably can't find it though. It's gone. It was there. Now it's gone. So let's just try a couple of these. Is LiBr soluble? Is LiBr soluble? Okay. Well, I look at it. Is Li an alkali metal? Yes, we're done. Because rule number 1 says anything with an alkali metal in it is soluble. We're done. Once we see that alkali metal, we don't have to worry about what the negative piece is. Is BaNO32 soluble? Well, is Ba an alkali metal? No. So now I got to look at the negative piece. Nitrate. Where's nitrate in our rules? The second rule, it said nitrates are soluble, right? So, because rule number 2 says nitrates are soluble, so that will not make a solid. That'll dissolve in water for you. CaSO4. Is Ca an alkali metal? It's alkaline earth, isn't it? Okay, so then we got to look at SO4. What does it say about SO4s? Sulfates are soluble except if they're with. Is calcium on the list? No, calcium's not on the list. So we go with the first half things. It's soluble, right? Actually, but number 2 was yes, wasn't it? Why did I put? Yeah, why did I put no? Okay, and that was the one about sulfates. Okay, how about PbCl2? Is it soluble? Is Pb an alkali metal? No. That's Rb. Okay. Cl's a chloride. What does it say about chlorides? Chlorides are soluble, except if they're with, and Pb's on the list, that's the except, right? So it will dissolve unless it's with those. So this will be right. It was one of the listed exceptions on our solubility rules, right? So everybody see how that works? CaCO3. Is Ca an alkali metal? No. CO3 is a carbonate. Rule number 5 says carbonates are insoluble. Because carbonates are insoluble. That was on the list of all the negative ions. What about K2CO3? Is K an alkali metal? Yes. That's it. We're done. We're done, right? Once we figure out alkali metal, so don't forget to check that first piece. It'd be really hard, huh? Well, actually, oftentimes there's going to be an alkali metal on the other side. because we had to make everything dissolve on the first side before I mixed them. Before I mixed them, I had to make them soluble. So I used lead nitrate. All nitrates are soluble. And potassium iodide starts with potassium. Okay. So CD. CD. It's not an alkali metal, so I got to look at the negative. That negative piece is, it's a chlorite. Chlorite wasn't, oh, that's chlorate. Sorry, it is chlorate. Yeah, chlorate. What does it say about chlorates? You say they're soluble or insoluble? Soluble? Chlorates or chlorides? Chlorates or chlorides? Which one was it? Yeah, it's rule number 2. Chlorates were in the list. Okay? Chlorates were in the list. So, chlorates were in the list. So this is soluble because of the chlorate. Are we okay with that? Okay, so now let's talk about that reaction. It's actually, you can actually see the stuff falling through that other layer. See why I use the down arrow? Right to the bottom, it's fallen as it gets near that interface. Okay, so what's the yellow stuff? Say, well, how the heck am I supposed to know? Well, you write the equation. Okay, we write the equation. What did I put together? I put together lead 2 nitrate and potassium iodide. Those are the two things I put together. That yellow stuff's got to be something on the other side because those two were clear. So PB is going to end up next to I, and K is going to end up next to NO3. K is 1 plus, NO3 is 1 minus. That's KNO3. I is 1 minus. To get lead's charge, I have to go over here. Over here, lead was 2 plus. I said lead 2 nitrate. So that's got to be a 2. That's got to be a PBI2. Okay, so we know at least one of these two is a solid. Ever see how we know that? Okay. So PB, is it an alkali metal? No. So I gotta look at the negative piece. Iodides, what does it say about iodides? Not a single thing. But which one would apply to iodides? Which rule would apply to would you expect to apply to iodides? Why would you apply 4 to iodides? Chlorides and iodides should behave about the same. Is that fair? If they're in the same column, we expect them to behave about the same. If it had been fluoride, we'd expect the same thing. Okay. And it says chlorides are soluble unless they're with lead. So this is a solid. But it could be they're both solids. Is K an alkali metal?
Yes.
Yes. So we're done. So when I'm done reacting, what I'll have left is a solution of potassium nitrate and solid lead 2 iodide. And it's going to sink down to the bottom. Let's try one more. Oh, no, it's not. No, we're safe to eat. Let's go in the hazardous waste container. Lead causes dame damage. Okay, so there's the copper 2 sulfate you guys used, right? Since it was copper was low on the activity series, it got replaced a lot. Okay. So of course, and this is potassium dichromate in solution. It's a pretty color.